In section 4.4, we're going to talk about how to use the multiplication rule to find probabilities. So we're going to start with this procedure. We're going to roll a 6-sided die, and then we're going to flip a coin. And so, for example, we might ask the question, what's the probability of getting a 6 and then getting a tail? Okay, now think about it. Is this more likely or less likely to happen than just one of them? Well, since we're wanting two things to definitely happen, this is less likely. So we're going to create a probability tree to first look at this. So first, if we roll a 6-sided die, our possibilities are 1, 2, 3, 4, 5, or 6. Okay, and then if we flip a coin, off of each of those, we could get a head or a tail. Okay, so our probability of getting a 6 and then a tail, well, if we look, we have a total, our sample space, we've got a total of 12 things. We could get a 1 and a head, a 1 and a tail, 2 and a head, 2 and a tail. So there's a total of 12 things in our sample space, and there's only one way that we get a 6 and a tail, so it's a 1 in 12. Now compare that to getting a 6 would just be a 1 out of 6 chance, and getting a tail would be a 1 out of 2 chance. Okay, well, what if we want to get a number less than 5 and then get a heads? Well, how many are there things, that work like that? We'd have a 1 and a head, 2 and a head, 3 and a head, or a 4 and a head. So that means there are 4 out of 12, or a 1/3 probability. Okay, now that's compared to getting a number less than 5 would be 4 out of 12. And getting a head would be 1 out of 2. Sorry, this would be 4 out of 6 for getting a number less than 5. Okay, now say we wanted to find the probability of getting an odd number and then getting a tail. So here we could have a 1 and a tail, or a 3 and a tail, or a 5 and a tail. So this is a 3 out of 12 probability, or 1/4. Okay, so that's compared to getting an odd number would be 3 out of 6, or 1/2, and getting a tail would be 1/2. Okay, so maybe you're already seeing some patterns about how we can take the two of these things and get our probability of those two together. Okay, so we need a definition. So given a random procedure, 2 or more outcomes or events of the procedure are called independent if the outcome of the first does not affect the outcome of the second. So if the first one has no effect on the second one, then they're independent. So for example, on the previous page, rolling a dice and flipping a coin, the dice roll has nothing to do with the coin flip, so those are independent. Now, when two things are independent, the probability of A occurring and then B occurring, we multiply their probabilities. That's why it's called the multiplication rule. So the probability of A and B is the probability of A times the probability of B. Okay, so let's say we roll an 8-sided die 4 times, and we want to know what's the probability we get a 6 all 4 times. So another way of saying that is what's the probability we get a 6, and a 6, and a 6, and a 6. Now, rolling the dice, the second roll has, the first roll has no impact on the second roll, and so on. So this is an independent case. So the probability of getting a 6 the first time is 1/8, times the probability of getting a 6 the second time, 1/8, times the probability of getting a 6 the third time, 1/8, times the probability of getting 6 the fourth time, 1/8. So here our probability is 1/8 to the 4th, which is 4,096. Okay, and then we can do a similar one here. Find the probability we get a 2 all 4 times except the third time. So that means we want a 2, and then another 2, and then anything but a 2. So we'll say not 2, and then another 2. So the probability of getting a 2 the first time is 1 out of 8. The probability of getting a 2 the second time is 1 out of 8. The probability of not getting a 2, well, there's 7 things that aren't 2 out of 8. And the probability of getting 2 the last time is 1 out of 8. So here our probability would be 7 over 4,096. So on question number 3, it says the probability that a person in the United States has type B negative is, this is blood type, is 1.5%. 3 unrelated people in the U.S. are selected at random. So we want to know what's the probability that all 3 have type B negative blood. So here we'd want person 1 to have B negative, person 2, and person 3. Now 1.5% as a decimal is 0.015. So we're going to multiply these together because they're independent since they're not related. If they were related, we'd have to find out some more information. So the probability that the first person has B negative is 0.015 times the probability of the second person times the probability of the third person. So this is the same as 0.015 cubed. So here we get 0.000003375. Okay, so your calculator may put this in scientific notation, but we can change it to a decimal. And then, so as a percent, this would be 0.0003375%. Very, 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 very small. Okay, what's the probability that none of them have B negative blood? Well, so if the probability of someone having B negative blood is 1.5%, not having B negative would be 1 minus 1.5%. Sorry, 1 minus 0.015, which would be 0.985. So the probability that none of them have B negative would be 0.985 cubed. So here we get 0.9557, or 95.57%. Okay, now we have to talk about if 2 things aren't independent. So the opposite of independent is dependent. So 2 things are dependent if the outcome of the first does affect the outcome of the second. So for example, if you were drawing a card out of a deck and you then didn't put it back in the deck, your deck has now changed, and so whatever happened the first one has changed the probability the second time. So now if 2 things are dependent, then the probability of A and then B is the probability of A times the probability of B given A. And B given A means that we want to find the probability of B, so probability of B happening given that A has already happened. Okay, so we're going to assume that A happened and then find the probability that B happened. So problem 6 says at one point in American history, there were 87 men and 13 women in the U.S. Senate. So the Senate has a total of 100 senators. 3 senators are chosen at random to be on a special committee. We want to find the probability that all 3 senators on the committee are women. So once we choose one person, we can't choose them again. So they're kind of pulled out of the pile. So this is a dependent situation. So the probability that the first person chosen is a woman would be 13 out of the 100 senators. Well, now that she's already been chosen some woman, we only have 12 women left out of 99 senators to pick the second person. And then for the third person, we only have 11 women left out of 98 senators. So we get 17, 16, out of 970,200. And we can reduce this to a 13 out of 7,350. Okay, and so this would be approximately 0.18%. So very, very small chance that all three would be women. Okay, now here's the other place where dependent probabilities come out when we're not replacing something. So it says there are 5 colored dice in a bag. 3 are red and 2 are green. 2 dice will be drawn from the bag without replacing them. So after we pull the first one out, we leave it on the table, and then we reach back into the bag and draw the second. So first we want to find the probability that both dice are red. So the probability that the first one's red and the second one's red. So if we, just the regular bag, for the first one, we've got a 3 out of 5 chance of getting a red. Now, we assume that we've already pulled a red out. That means there's only 2 red left in the bag and 4 dice. So that means there's a 6 out of 20 or a 3 out of 10 probability of getting both red in a row. Okay, and then we have find the probability that the first dice is green. So the first dice being green will be 2 out of 5. And the second dice is red. Well, the first one is green, so we still have all 3 red in the bag. And now we only have 4 dice left in the bag. So again, we get 6 out of 20 or 3 out of 10. So when you're using the multiplication rule, it's really important to know if your situation is an independent situation or a dependent situation.